All right, let's take a look at section 14.6, which will cover the directional derivative, and more importantly, the gradient. So just a couple of learning objectives. I will define the gradient and the directional derivatives, and then we'll use both of those to calculate directional derivatives. Starting off with the definition of the gradient. So if f is a multivariable function of x and y, then the gradient of f is a vector function where each component of the vector is just the derivative of that original function f with respect to the variable in that position. So in 2 dimensions, it's the x partial derivative in the x coordinate, or the x component, and it's the y partial derivative in the y component. If we have a 3-dimensional vector, or a function of 3 variables instead of a function of 2 variables, then that gradient is just all 3 derivatives, x, y, and z in each component. And again, we go from a scalar function f to a vector function gradient of f. So the gradient takes, again, a scalar function and turns it into a vector derivative function. So the symbol for the gradient is that upside down triangle. I believe the name for it is nabla, but we'll oftentimes just call it del. So we can read this the gradient of f or del f. And the gradient of f is always going to be perpendicular to the level curves of f. So if we have some shape, like a surface, then the gradient should be normal to whatever surface we have. So again, if our function f describes a surface, the gradient is normal to that surface, or perpendicular to its level curves. So if we then define the directional derivative, at some point, we'll have a unit vector. In this case, we're looking at the 2-dimensional example. The directional derivative at some point ends up being the gradient dotted with whatever unit vector we have. So if we take the gradient of a function, that'll give us, it should give us a vector, a derivative of vector, a vector of derivatives. There we go. And then we'll take the dot product of that gradient with whatever direction that we want to go. And again, it needs to be a unit vector, meaning that the magnitude is 1. So the magnitude of our unit vector is always 1. That's what it means to be a unit vector. So we'll just take the dot product of that unit vector with our gradient. So in general, the directional derivative is equal to the gradient dotted with the u vector, where we're introducing a somewhat new notation here, the vector x. This doesn't just mean the x component of the vector. When we're going to call the vector x, that'll be the vector of variables. So it's just a handy way of writing out. And so we don't have to write, the vector x, y, z. We can just call it vector x, and then it just means all the variables. So in 3 space, that's x, y, z, or if we need to be more general, we just call it x1, x2, x3. And in 2 space, of course, that would be just xy, or x1, x2. And this will cut down on some of the notation that we need to use. So earlier when we introduced the gradient, I wrote it out once for each dimension, once for 3 variables, once for 2 variables. And with this new x vector notation, I can just write it once and then say for however many variables we need, it's just the variable vector, x bar. All right, enough of all that. Let's actually look at an example. So we want the directional derivative of the function z equals x squared plus y squared at 1, 1 in the direction of 1, 2. So if we've got z equals x squared plus y squared, that means we can have z equals f of xy. So z is a function of x and y, meaning that we can get the gradient of f and that gradient of f should be the vector 2x, 2y. Since we'll just take the x partial and the y partial of our function and put the x partial in the x coordinate and the y partial in the y component. So now that we have the gradient, the directional derivative, du of f of x is equal to the gradient f of x dotted with that vector. So this should look like the vector 2x, 2y, dotted with the unit vector, which will be 1, 2. And we need to make this thing a unit vector, so we need to divide it by its magnitude, the magnitude of which is 1 squared plus 2 squared. So all in all, this thing comes out to 1 over the square root of 5 times, let's see, this looks like 2x plus 4y. And now we just want to plug in the point that we actually want to calculate this vector at. So we're looking for that directional derivative at f of 1, 1, which looks like it ought to be 6 over square root 5. Or if we rationalize this thing, 6 root 5 over 5. All right, so if we want to maximize the directional derivative, so finding the direction where our directional derivative reaches its maximum value, that's going to be in the direction of the gradient. So we find our maximum value that occurs when u and gradient of x are in the same direction. The maximum value of that directional derivative is just going to be the magnitude of the gradient. So put another way, if our direction and our gradient are parallel, that means that our unit vector is equal to the gradient divided by the magnitude of the gradient. Similarly, if we need the minimum instead of the maximum, then our unit vector is parallel to the negative of the gradient. So parallel to negative gradient f. So basically just go backwards to find the direction of minimum change, go forwards in the gradient to find the direction of maximum change. So if we put that into an example, finding the maximum rate of change of that same function at the point 1, 1, and we want the direction that it occurs. Well, we already got our gradient in the previous function. So the gradient of f at 1, 1 should be the vector 2, 2. So this should be our direction. If we end up calling that a unit vector, then it's going to be 1 over the square root of 2 times 1, 1. If we need it to be a unit vector. Although if all we need is a direction, then I think either vector seems fine. Finally, getting the actual maximum rate of change, we just want the magnitude of the gradient of f at 1, 1, which should be the square root of 2 squared plus 2 squared. Since our gradient vector was 2, 2, and that thing comes out to the square root of 8, or 2 square root 2.